IPKISS comes with a powerful circuit simulator Caphe that allows you to investigate the performance of large circuits in both time and frequency domain. Caphe lets you simulate circuits that would be unfeasible with other methods such as finite difference time domain or eigenmode expansion. It does so by assigning a model based on S matrices and differential equations to each component and combining all this information to calculate the full response of the system. If every component in a circuit has a model attached to it, running a frequency domain simulation is quite simple. Let's start with the two-level splitter tree from the previous chapter as an example. As always, we first import the PDK, IPKISS, and any other dependencies we need. Because every MMI and waveguide in SciFab PDK already has a predefined model, we just need to instantiate the circuit model view of the circuit and call getSMatrix. The result is an S matrix describing the transmission between any two ports. We see that the power is split evenly among the outputs and there are some small reflections at the input. Running these simulations in a code environment provides interesting possibilities. We can, for example, use for loops to sweep a parameter's value and find out how it impacts the circuit's performance. This can be demonstrated with a Mach-Zehnder interferometer. We can see the layout to the right. We have an MZI with a path difference of 100 microns, and we have two electrical sections connected to the top and bottom arms which will act as heaters. We will sweep over a range of path length differences between the two arms of the MZI, resulting in different interference patterns at the output. The result for each value of the path length difference can be plotted. As the path difference increases, the free spectral range decreases proportionally as expected. We can also run time domain simulations. These are slightly more complicated than frequency domain simulations, and a full description of them is out of the scope of this Getting Started course. However, you can find more details in our Lucida Academy if you are interested. So we start by making a virtual test bench. Both arms of the MZI can be thermally tuned by applying a voltage to the electrical ports. If a constant optical signal is sent through the input while the voltage across one of the arms is steadily increased, we expect that the power level at the output will change over time. So to test this, we start by creating optical and electrical sources. We can do this by implementing i3.function excitation, and we then connect a probe at the output. As you can see, the voltage is applied to the bottom arm. The source and probe are connected to the input and output of the MZI respectively. As expected, we see the initial transmission is poor due to the imbalance in the path differences. As we apply our ramping voltage, the refractive index in the bottom arm changes, reducing the phase difference and resulting in a higher overall transmission. Now it's over to you. In your IPKISS PyCharm environment, you can find in the Getting Started material for this chapter an exercises.py file. Try to compare simulations with and without grating couplers and make changes. So in the PyCharm environment, you can open up exercises.py and follow the guidelines. You will see ellipses where you can fill in the details to complete the script. If you get stuck, we have a solution file for you. We now return to the generalized splitter tree from the circuit layout tutorial. As layout and simulation are tightly linked in IPKISS, because of how we implemented it, it's now possible to run a circuit simulation of a splitter tree with any number of levels. Everything changes automatically by simply changing one parameter, the number of levels of our P-cell. To visualize the final S matrix, we loop over all the output ports and plot the transmission. So in our IPKISS PyCharm environment, we can see this example here in the Advanced Examples section with the Explore Parametric.py. We have a 4-level splitter tree, which is defined with n levels 4 as an input argument, and some basic plotting. So if we just run this, we can see the results for the reflection versus wavelength. IPKISS also provides tools to analyze spectrums and extract various characteristics, like the free spectral range or the insertion loss. To demonstrate this, we'll extend the code from the tutorial where an MMI was simulated for a few path length differences. We don't need to change much, except that the S matrices are now passed to i3.spectrum analyzer. The spectrum analyzer calculates the insertion loss extinction ratio and free spectral range, and the results are saved to a dictionary, and the plots you can see on the right. We once again return to the IPKISS environment to the example script explore MZI simulation analysis.py, and here we see the sections we previously discussed. So where we store the results in a results dictionary, where we calculate the FSR and the plotting. So we run this script. And here we see the calculated path differences and the extinction ratio, insertion loss, and free spectral range plotted as a function of path difference. In this tutorial, we've looked at how to run frequency domain and time domain simulations using our powerful circuit simulator Caphe in IPKISS. For the time domain case, we looked at how we can do this with a virtual bench and using electrical and optical sources. And for analysis, we looked at parametric circuit simulation using a previous example, as well as using a spectrum analyzer. This enabled us to calculate the free spectral range, the insertion loss, and the extinction ratio. If you'd like to learn more, please visit our Lucida Academy for many more interesting examples. If you have any questions, please reach out to us at support@lucidaphotonics.com.